Because of my background, many of them that we've applied them to are aerospace problems. We've applied them to the evolution of the commercial transport, the two-engine commercial transport, A320, 737 that we all fly around in routinely. We've applied them to human exploration of space, to Earth observation from space of the Earth. We've applied them to several oil and petroleum projects, including refinery design and development, offshore exploration for oil, and other exploration for oil in other complex environments, and space communication. So what these techniques do is they allow us to look through a very broad combinatorial set of options, of concepts, to pick ones that are desirable for further exploration. So the first thing we do is understand the stakeholder needs. So let's take the example of going to Mars, which is a problem that we've actually worked on extensively with NASA. The President actually just recently reaffirmed that his presidency stood behind the goal of getting to Mars by sometime in the 2030s, which is not that far away if you have to get to Mars, by the way. So the first thing you do is functional analysis. What are the set of functions that have to be executed to get from here to Mars with humans and back? You have to launch from the surface of the Earth, you have to rendezvous and assemble things in Earth orbit, you have to propel yourself out of the Earth, you might stop at a libration point in the Earth-Moon system, you might go to the orbit of the Moon, you might get a gravity assist off the Moon, then you head towards Mars, you enter Martian orbit, you get ready, you descend to the surface to deploy assets, and you can see step by step there are many functions that have to be executed. And some of them can be combined and some of them can be sometimes omitted. Then you have to think about what pieces of form, what actual items of structure, of substance you're going to build in order to execute these functions. And then you have this large combinatorial space that you search through analytically. You model each of these pieces so that you get an array of possible solutions, which then you can evaluate by things such as the risk of mission success, or the risk of mission failure, I guess, the probability of mission success, the cost in some crude metric. And they produce a Pareto space of possible solutions which identifies the desirable ones for further development. And the validation of this is that the other approach, which is to put a team of very skilled and capable and experienced people to work on a point design, what's essentially a point design, maybe with small variations, will produce a much more detailed analysis of 1 or 2 or 3 or 4 point designs. So if those 1 or 2 or 3 or 4 point designs are well represented in this space of perhaps thousands, tens of thousands of options that we develop, then it validates that this is a reasonable analysis. And you can assume that the other points that are highly desirable designs are likely to be worthy of consideration as well. Yes, there is a generalizable approach. First, it's all in software, and this is all computational. So you build models of the network of events, and you build models of the pieces of form, the instruments of the structure that will actually execute these sequence of events. And then you combine these in all the possible viable combinations into an integrated system, which you might get millions or tens or hundreds of millions of examples of. And then you evaluate the performance of each of those tens of millions of examples, and you pull out the desirable ones. So that's the general pattern. And the reason the problem is difficult is in these real situations, there are actually many internal functions and many assignments, and then all of those things multiply combinatorially. So there's
2 zillion ways to get
yeah, right. And in fact, there's another good example that we did as a sort of historical benchmarking. We did this about 10 years ago, is we ran the analysis for going to the moon in 1961. So we knew exactly what decisions the people who were planning the Apollo mission had to make and which ones they struggled on, and we were able to represent that. So would there be a lunar orbit rendezvous? Would there be a separate spacecraft that went to the lunar surface? What sort of propellants? How big would the crew be? What sort of launch vehicle would you use from Earth? And since this was 10 years ago, we were fortunate in the sense that many of the original decision makers were still alive from the early 60s. And they were able to recount to us by actual discussions with them what the decisions were, which ones they made and which ones they didn't, and why. So we were able to take all this information and the information that we had only in 1961, not when the mission was successful in 1969, to recreate the decision space that they went through and actually, interestingly, identify the three dominant designs that were proposed. There was the design by von Braun, which was to build a massive rocket, much bigger than the Saturn V, and fly a spacecraft all the way to the surface and back. There was a design proposed by a fellow named John Hubolt at NASA Langley, which is what we did, Lunar Orbit Rendezvous, a capsule and a lander. And there was a design created by Korolev, the Russian designer, the Russian general designer, which was to do a similar two spacecraft mission, but with only one pilot went to the surface and one pilot who remained in lunar orbit. So it was a smaller, lighter mission. So the three dominant designs actually appeared, interestingly, on this frontier of good options.